So welcome back. So here we will look into some of the very basic design considerations. So for so in this thing, in the same engine, if you want to design for a large Mach number range, that is, say, from Mach number 3 to Mach number 15, then you have to have a range where it operates, basically you can operate in a ramjet scramjet mode, which is called the like a dual mode scramjet, and then you can operate it in a pure scramjet mode when the Mach number is greater than 7. Okay, so in the dual mode scramjet, what you have is essentially you have the air coming in, and then you have this through this shock trains, the flow gets compressed, and then you have the constant area isolator. And the flow that can essentially happen can be subsonic in some parts, and then you add fuel, and then this can be a ramjet combustor. Okay, whereas in the pure scramjet mode, this air passes through this the shock structure is of course different, because you have a Mach number much higher, and then this shock trains are prevalent even in the isolator, which contains the shock trains, and then you have basically add heat, you basically add fuel much upstream, because now you see that this has much reduced flow residence time scales. So you add fuel even before the isolator itself, and then you can have a design. So one of the major considerations is that there are two things, that's like the length of the isolator, which can contain the shock train, and the divergence angle and the length of the combustor. Okay, so we'll not, as I said, we'll not go into these details, but these are the main things, and there are like several correlations as well as empirical relationships, semi-analytical relationships that are there. But there are people basically can use essentially three type of methods. One is the integral method, that like the Rayleigh flow analysis that I showed you. One can use the differential equations to solve the different processes of the same things, but essentially the processes, the equations that you need to solve are essentially the mass, momentum, energy, and in if you want, you can, species equations can also be invoked, and even if you want to do further analysis, you can of course use CFD to do the design. So the integral analysis is mainly used to do the assessing the experimental data and understanding of the key interactive forces, features, and the development of a preliminary design information, and provide engine performance analysis. So provide engine performance assessment. So these integral analysis, this even if they are 1D or very rudimentary, this is extremely important and must be carried out before going into any sorts of complicated analysis. Okay. So typically one can also couple, this comes from Billig's paper, scramjet combustion processes. Sorry, combustion, this comes from this paper, combustion processes in supersonic flow by Billig, is one of the pioneers of scramjet. From this JP, Journal of Propulsion Power, in 1988. So what he says is that one can essentially couple the integral method and the differential methods to solve, to develop a design. So the integral method should give you the pressure distribution, and then that can the pressure distribution, but some of the integral method needs to be fed with the wall shear model, the wall friction model, the wall heat transfer model, the combustion efficiency model, the shock train model, there can be base pressure model. All these things should go into the integral methods. Okay, and then the integral method can provide you the pressure distribution, the pressure rise inside the combustion chamber, and then you can feed this information into the finite difference method. So the finite difference methods, because it's like you can incorporate the rate kinetics model, turbulence model, etc., and then you can have the combustion efficiency, and this can lead to many other things also. But then this can be used to refine your integral analysis itself. So in this coupled manner, in an iterative manner, the whole analysis process might evolve. Okay, for the integral analysis, the equations that you need to solve are essentially this the continuity, energy, and the momentum equations. So this is your continuity equation. So where do you have so this is the, say, between, say, two stations A and this is between two station A and B, your total mass flow rate at station A plus the mass flow rate of fuel, that is equal to the mass flow rate at station B. The pressure, the force arising due to pressure differential must be balanced by the inertia forces, and that due to the fuel. And also there has to be like losses that can arise due to the friction as well as the fuel injection. So whereas this AB FW refer to the control volume, entrance, exit, fuel and wall respectively. So the whole, this is the force balance inside the combustor, that is, this is, or the momentum balance. Change of momentum balance or force balance. So this is the force arising due to the pressure forces at the inlet and the exit. This force W sin alpha arises due to the fuel and the wall interactions. This is the shear stress that arises due to the from the walls, and this is the inertia force changing due to the flow acceleration or deceleration, and this is due to the fuel injection. Okay, so these are the forces, and then you can have of course you have to use the energy balance, where the total you see, this is the stagnation enthalpy at exit at station A, and this is essentially the stagnation enthalpy at station B. Of course, the fuel mass fraction needs to be added, and this is the fuel stagnation enthalpy, where F is the fuel to air ratio, and of course this is the heat addition because of the additional enthalpy that the fuel brings in with itself. Okay, so so F is essentially your m dot F by m dot A, that is a fuel to air mass flow rate ratio. So using this integral analysis, one can essentially derive the different design the engine. But of course, it, as you see, that this is much more complex. One of the things that is needed is that the pressure area variation, because you see that the area at section A and area at section B is not same. So the areas essentially has to have a divergence to accommodate the addition, the heat addition in the supersonic flow. So for that, people use different things, like there are like Crocos pressure area tailoring, like P times A divided by epsilon minus 1. So whereas epsilon can be equal to 0, 1 and a minus gamma m square, depending on whether it's a constant pressure process, whether it's a constant area process or a constant Mach number process. So those things are people do additional empirical correlations that people induce to develop this design. But it's essentially the solution of these three, moment, continuity, momentum and energy balance, that gives rise to this that with which one can go into the design analysis. So once again, this to remind you, these are the scramjet processes that which are of interest to us. That if we are looking into the isolator and the combustor part, that of course we have a shock train, and downstream of the shock train we inject the fuel, and the fuel must mix before it can burn, and before it can burn the fuel must ignite. So mixing, ignition, burning, these are the most important processes inside a scramjet combustor. Okay. So as such, combustion in scramjets, this is challenging because of the large variation in thermodynamic conditions. Okay, as I said before, that in a gas turbine combustor, the flow is essentially conditioned by several things. That is, passes through a series of compressor blades, rotostator blades, and then it comes to through the diffuser, and then it goes into the to the combustor. So the combustor entry conditions are pretty much well defined. It cannot vary too much. Whereas in a scramjet, there is no such rotating or machinery to control it, and it's only the cross section radius that changes it. So, any small change in the upstream downstream can lead to a variable or even in the flight parameters like the flow speed changes, etc. Those things can also lead to a large change in the combustor entry conditions, and the variation can be both in thermodynamics as well as in the flow parameters. Okay. Now at a low Mach number, the thing is that at low Mach number the heat deposition in the combustion chamber is larger than the incoming flow energy. Okay. But then as a result of that, the pressure rise is also higher. Okay. And there are like more chances of like upstream shock formation. Okay. So as a result of that, the flow speed is reduced because the heat release effect is very strong here, and that can lead to very large pressure rise, and that can also lead to flow separation. Okay. So it does not mean that the low Mach number operation of a scramjet is simple. Okay. That is, a Mach 2 operation is not simple, whereas at higher Mach number, the thing is that your heat deposition in the combustion chamber is smaller than incoming flow energy. For example, at Mach 25, if at all it is possible, there is no such Mach 25 scramjet engine, whereas the heat addition is only 10% of the incoming flow enthalpy. So this is not really useful. Okay. And effect of heat addition is much less pronounced, but then why will you operate a scramjet engine at a Mach 25 when the heat addition is only 10% of the flow enthalpy? So it's simply not worth it. Okay. And the another thing is that the complex aerothermodynamics coupled with combustion. Okay. So here you see that just before that, before combustion happens, there is a series of shock trends. Even inside the combustion chamber of a scramjet engine is characterized by several kind of like oblique shocks, expansion fans, and shock boundary layer interaction. These are ubiquitous in a scramjet combustor. So the aerothermodynamics is really complex, and the combustion process cannot be learnt, the mixing and the combustion process cannot be learnt in isolation from this complex aerothermodynamics and the shock combustion interaction, shock boundary layer interaction. So one has to understand this in a much more integrated manner. And another thing is that the mixing time and the chemical time scales are comparable, and it is comparable even with the comparable even with the flow residence time scales. Okay. So mixing the flow residence time scales, the mixing time scales and the chemical time scales are all similar. Okay. So the mixing and the chemical time scales are similar, so that means that there is very strong turbulence chemistry interaction. When the residence time scale and the mixing are similar, when the chemical time scale is similar, that poses great challenge to flame stabilization. So these are the different challenges that one encounters in a scramjet combustor. So what are the key processes? If we look into the scramjet combustor, apart from the aerothermodynamics, that is in terms of the combustion itself. So if you say that the combustor has a total residence time of about 1 milliseconds, so of course you need to have thermal management of fuel. If you are using a liquid fuel, so then of course you have to there has to be breakup. The liquid jet must break up. There must be atomization. There must be dispersion. Okay. And there must be, then you have to have evaporation, then you have to have mixing. The mixing is actually a very long process. Okay. And then you must have ignition delay, so that you must have ignition, and that takes some time, and then you have flame stabilization. So all these processes you see take time, and all these processes has to be completed within this 1 milliseconds, but all these processes, this processes functioning properly in an interacting manner is required to generate the thrust. Okay. So all this process must function perfectly, and they must function satisfactorily within 1 milliseconds, so that proper thrust can be generated. So this is the basic biggest challenge of a scramjet engine, that you have to have all these processes done in a very short amount of time, which is extremely challenging. So we will go into mixing. The mixing is a very important process inside a scramjet. Okay. As you see here, that mixing is a very important process, and mixing as such is the process, often is the process that takes most amount of time. Okay. Now mixing is a critical process. Why? Because we all know that combustion cannot happen, it cannot even be initiated unless fuel air mixing at a molecular level has been achieved. Okay. Now, we cannot study mixing in isolation inside a scramjet, because ultimately your mixed fuel air mixed state must undergo combustion, and when it undergoes combustion, the local temperature, density, diffusivity, viscosity, everything changes, okay, and then that affects mixing itself. Okay, you will see that mixing essentially in this scramjet combustors are controlled by essentially shear mixing layers and large roll ups of the shear layers, and of course very strong turbulence mixing is there. So all these processes essentially control the mixing and the subsequent combustion. So in this scramjet, you can say that mixing happens through diffusion. It happens through parallel layers of different velocities, densities, and chemical composition, or it happens to vertical mixing, and of course it happens to turbulence. So if we consider the mixing in shear layers, so what is a shear layers? Shear layers is essentially that region in the flow which is characterized by strong velocity gradients, and essentially which results in strong shear forces. Okay, and that is caused by that happens when you have two parallel layers which are moving at different velocities, okay, as in this case. So in that case, if you have two parallel layers moving at different velocities, u1 greater than u2, one moving with u1, another moving with u2, and u1 greater than u2, then you will have a shear layer developing between them, and this is governed by the shear layer thickness. Now the Reynolds number that is typically characterized used to characterize is essentially this delta u times delta, which is this shear layer thickness divided by nu, okay, and whereas delta u is essentially u1 minus u2, okay. And then of course when you have this kind of a situation, then this shear layer does not develop like this itself. What happens is that it leads to development of these instabilities. Here you see like a Kelvin-Helmholtz instability we formed, and when there is instability, there is a large scale vortex roll up, and you see that this is one fluid, this is another fluid. Of course there is velocity difference between them, and there is composition difference between them, and you see that how mixing is happening. There is not much mixing happening through here, but as this rolls up, and then there are like large strainlets formed, and then there are, because of the when there is a large species gradient and large velocity gradients, then you see that mixing is happening along these regions, okay. So it is this type of like roll ups, vertical roll ups, that assist in mixing when in high speed flows. Eventually it is there has to be diffusion that at the smaller scales which has to mix the two fluids, but then the diffusion process is assisted by creation of this large species gradients, which is accomplished through this different roll up of this of these different structures, which assist in creating this large species composition gradients in the flow itself, okay. So this is the thing, and where you see in this we can do different kinds of analysis. You can define a convective velocity, which is the velocity of this vortices that are moving, etc. Now one of the things that here we want to understand the effect of compressibility on shear layer growth, okay. That is you can define, as I said, that you can define a convective velocity here, and which is the velocity of this vertical structures which are moving. Now if this becomes large Mach number, okay, that which is typical in a scramjet engine, how does really the shear layer development happen? Now why are we interested in the shear layer development? Because even if there is composition difference, the mixing layer that will be formed, or the reaction layer that will be formed, will be essentially embedded inside these shear layers. So this embedding, we need to understand what happens, what is the thickness of the mixing layer, or what is the thickness of the reaction layer. A bigger parameter is essentially the shear layer, okay, this thickness. So since this reaction layers, mixing layers are always embedded in the shear layers, it is of interest to know how does even this shear layer develop in this kind of compressible flows. As such, it turns out that it's very non-intuitive, that if we define a convective Mach number like this, where mc1 is equal to u1 minus uc, whereas uc is the convective velocity divided by the sound speed and the fluid 1, that is this is the fluid 1, and this is the fluid 1, this is the velocity of uc, Okay, and if we define a convective Mach number based on that, which is defined as the difference between u1, that is the free stream velocity of 1, minus uc divided by a1, and that is my convective Mach number. And if I plot the delta by x, that is the shear layer growth, this as a function of distance at MC1 as a function of Mach number, we see that after Mach number equal to 1, this essentially asymptotes. So there is not much of a shear layer growth. The shear layer growth is important for mixing because once the shear layer becomes very large, then essentially that is where inside which the two fluids essentially meet and can mix. Okay, so but this is kind of an asymptote at about Mach number of starting at which is reached at a Mach number of 2, says that the compressibility essentially has a limiting effect on the shear layer growth and the corresponding mixing. So one cannot rely only on shear layer development to achieve mixing. One has to think of some other processes also in a compressible flow. Now, as such, there are more to mixing within a shear layer, whereas Demotak is suggested that that it is essentially the local Reynolds number, which is this guy, can define the mixing within the shear layer, or the development of the mixing inside the shear layer can be developed, can be defined by this. Now, but the thing is that he said that there exists an initial region of unmixedness. Okay, so just after the shear layer is developing and this large scale roll ups are happening, it does not mean that mixing start immediately. Okay, so he says that there is an initial region of unmixedness, and which is this region of unmixedness is called the mixing transition length. So there is no mixing in this mixing transition length, or very limited mixing. Now the reason is that there is this, at this region, this large scale structures develop and they entrain initially unmixed fluids. So for this, the large scale structures essentially roll up, and so they create the strain on this the fluid elements, and essentially create large gradients through which mixing can happen. But then that takes some time to develop. Okay, so only this fluid mechanical development of large scale structures immediately does not allow for mixing, and only after this development some straining has been inflicted and some large gradients of species has been formed, then the mixing can start. So as you said here, that at the end of the mixing transition length, the turbulent structures in the shear layer evolve. As the shear layer develops, the Reynolds number also increases, so it undergoes there is a turbulence also develops, and these turbulent structures in the shear layer have evolved to a degree that allows mixing at a molecular level to begin. As you know, turbulence helps in mixing through similar to an energy cascade process. That is, first this large eddies are formed, and then this creates essentially large strains the different the fluid, and this as the fluid is strained, then this the gradients become large and large. Okay, so even if there is a large gradient, so the way turbulence mixes is that if you have a large gradient of a species of a scalar, so essentially turbulence creates large scale structures, which really does not help in mixing, and as it is. But then these large scale structures develop into small and small scale structures through the cascading, and as this cascading happens, this small scale structures have very large strain rates. So this large strain rates essentially creates stretches the fluid, and this, as the fluid is stretched, it develops composition gradients across the two different species, and then at the small scales these composition gradients can essentially diffuse by molecular diffusivity, and then these two can mix. Okay. So mixing essentially is a small scale phenomena in turbulence, and because ultimately it is diffusivity or diffusion that has to control the mixing. But then what turbulence can do is that because of this multi-scale and the cascading processes, it can quickly form the small scale structures from the large scale structures. So by which the mixing is essentially enhanced. Okay. And of course, you can see that the turbulence has a diffusive, very strong diffusive nature also, that if you have two particles in a quiescent environment, if you have a large cloud of particles in a quiescent environment, they essentially their distance, the dispersion, the pair dispersion distance, that is the distance between any two particles, statistically changes like as a function, as a proportional to t, proportional to time. But if it is turbulence, then this distance squared changes proportional to t squared or t cube. So as a result, the turbulence essentially is very diffusive in nature, and it that also helps in the mixing. Okay, so but then, as I said, that we cannot only rely on the shear layer mixing, because in compressible flows, shear layer has a limitation, because at Mach number this shear layer growth becomes limited. So one can often use this transverse flow mixing also, where they essentially inject. So if this is a flow coming, so they inject perpendicular to the flow, and a jet forms like this. Okay, so that is called a typical like a jet in a cross flow. But when you but if this flow is supersonic, and even if this jet is under expanded, that really leads to a very complex fluid mechanical and shock structure, fluid mechanical structures developing all around it. Now, as you see in this model of a transverse under expanded jet in a supersonic stream, this this first injected stream forms a barrel shock, and that generates this bow shock around it. Okay, essentially we think of the bow shock as a two-dimensional structure, but here you see it's essentially because the flow field is very strongly three-dimensional, it is a full three-dimensional structure, the bow shock that has formed, and it leads to formation of this recirculation region in front of the jet. And these vortexes spill around this around the barrel shock, and this bends in the and also this jet bends in the downstream direction, because there is a very strong momentum of air that is coming, which immediately bends the jet. And there is additional recirculation zone forms in the both recirculation zones are formed both upstream and the downstream locations, here and here. And the downstream injectant angle relative to the supersonic airstream decreases, and the turbulent shear layer forms when the mixing continues. And this is facilitated by the streamwards vortices spilling off from the injectant plume. So it's a very complex structure that you can see that there are recirculation zone forms here, recirculation zone formed here, and there are vorticity structures formed around this. So it's a complex structure, but then this leads to very nice mixing because of the strong interaction of this jet into the incoming flow. And this jet penetration is often given by the ratio of the dynamic pressures, and often this is the height of the Mach disk with respect to the wall, and this is the diameter, and this is the ratio of the dynamic pressure of the jet divided by the dynamic pressure of the air, and it scales like the Z by D, the height from the wall is divided by D scales like the ratio of the dynamic pressure of the jet to the air to the raised to the power of 0.5. And you see that this is how the jet penetration trajectories in this Z, which is the height from the wall, bottom wall, varies according to x. So this is how typically, and there are several correlations that one can find in literature to develop this jet trajectory. Okay, so it is of important to understand how this, where this jet is going, because you need to ensure or need to inject the jet in such a manner that it goes into the region where you want combustion. So this formulating these jet trajectories and characterizing this jet trajectories experimentally and analytically is of very high interest. So with that, the gaseous mixing is we have covered, and then in the next in the next classes we will cover the liquid jet injection and the essential features of the combustion process in a scramjet engine. So till then, goodbye. Thank you.